Also scaling the bottom and adding adding the corresponding components. C1 e to the 2t plus 5c2 e to the negative 2t. So these would be the two solutions for x1 and x2. So x1 would be that. x1 of t is that function. x2 of t, that function. So we've solved both of those simultaneously. I'll just notate that here. Notice no bars over these guys. Okay, these are the individual functions at the beginning of that system. Okay. Only write the bars when we have it written in dense format, where x represents that column x1, x2. Okay. So we can define the Wronskian again. If I have solutions to a linear system, we can define the Wronskian. It's similar, but in some cases a little bit easier. So the Wronskian of these vector, those are the vector functions, is defined as follows. x1, x2, and it takes in, those are vector quantities, again, vector functions. So it is still determinant, and one way to write this in compact form, I'm going to write x1 bar, x2 bar, where these represent, I'm going to write these as column vectors in the actual determinant. Okay. In other words, I'm going to write them downwards. So x1 was e to the 2t, e to the 2t. So that's x1 as a column vector in this matrix. And x2 is, what's x2?
E to the
negative 2t.
And 5 e to the negative 2t.
5 e to the negative 2t. All right, and it's just the determinant of that matrix where the columns are the actual vector functions. So the general solutions to the system, the two solutions. All right, and to find a determinant product, so I get 5e to the what? E to the 2t times e to the negative 2t.
It's 1 over 5.
Right. Though those powers add, right? And 2t plus negative 2t gives me
0.
e to the 0 minus 1 e to the negative 2t plus 2t, 0 again. In other words, we just get 4. And that's not 0.
What does it tell us if it is 0? That it's
If it is 0, then
linear
those are,
independent?
right, and those two column vectors that represent the solutions to the system are linearly dependent.
They're not actually distinct solutions.
Right.
C1, C2, it's just...
It would be a constant multiple.
And then you get E to the 2t,
Mhm.
or...
Right, and 0 means that these column vectors, not parallel, right, not parallel. They're absolutely not, because they're linearly independent. Two vectors that are parallel, if you have two parallel vectors, even if they're vector functions, it's a scalar multiple of the other.
Oh, that makes sense.
So the column vectors here, x1, x2, are linearly independent. Okay. So when we're talking about vector systems, the Wronskian is a little bit different. I just lay down those particular solutions vertically, column vectors, and find the determinant that way. I don't know why it's different. I was asking someone else about that. I didn't really get an answer. Why it's different than the Wronskian of if we had 3 individual solutions to a particular equation, why we put in F, G, H, or whatever they are, Y1, Y2, Y3, and then it's derivatives after that. And so I don't know why that is. All right, but one thing I want to point out to you is, take a look, and let's open this up, see the theorem 1, page 2, is that 94? Principle of superposition. That fancy word is what we call, well, if I have n solutions to a differential equation, then any linear combination of those solutions is also a solution. And that holds for systems as well. So this reads a lot like a corresponding theorem in chapter 3. Okay? So if you have x sub 1 through x sub n solutions of a homogeneous linear equation or system, right? Okay. On an open interval, where all these are constants, then the linear combination is also a solution. And if you flip the page, here's the Wronskian defined, right? Okay, x1, x2, xn. On the next page, 296, the general solution. This is, again, corresponding to the same theorem in a single equation. It says that if you have n linearly independent solutions of a homogeneous linear equation, and this is a vector equation, so it is representing a system, this P of t matrix, that's just the matrix of coefficients. In this case, we're talking about constant coefficients. So that would be a constant matrix of constants. But what it says is if another x of t represents any solution, then that x of t must be a linear combination of those n linearly independent solutions. So that theorem also holds over from single equation case. Okay? So we're not going to do any, like I said, we're not doing any proofs of those or anything like that, but not here. Okay. So what if there were initial conditions to this system? If they're, when they give you initial conditions, it's going to be in a vector form. Okay? So that vector of solution functions, x, evaluated at some point equals b. They're not going to give you a single value b, but it's a vector of values. So this represents, if it's a system of 2 differential equations, then the b would be the column vector of 2 constants. Okay? If it's an nth degree, then what it looks like is x sub 1 of a, x sub 2 evaluated at a, x sub n evaluated at a. That is x bar evaluated at a equals this column vector of constants, b1, b2, bn. Okay? So there would be, this does contain n initial conditions in that vector statement. Okay? What it means is x sub 1 of a equals b1, x sub 2 of a equals b2, and so on. So it is in initial conditions in that vector form. All right, so in the previous, let's look at the previous example and say we had gotten this this particular initial condition. Say we are given that x bar takes in 0 and spits out 1, 3. Okay? So from equation 2, right there, so from that equation, let's look at what this initial condition looks like. So we'd have C1, equation 2 right here, yeah. So plugging in 0 for t, it gives us C1 x1 bar 0 plus C2 x2 bar 0 equals 1, 3. All right. So x1 of 0, remember that solution, what's x1 evaluated at 0? The solution x sub 1?
Just C1, right?
Right here. Yeah, put in 0, you just get 1, 1. Plus C2 and x2 of 0.
1, 5.
x2 gives you 1, 5. So it kind of gives you a vector of initial condition. So, and this was 1, 3. Okay, so breaking this out of its format for a moment, this gives us, it would be C1 plus C2 equals 1, right? Constant multiple. So scalar multiple of this, and I'm adding corresponding components, must equal 1. And C2 plus, or C1 plus 5C2 must equal 3.
Which is all in the matrix right there.
What's that?
That could be another matrix system right
It
there.
is. It is. And with all these matrices running around, let me get on to the next page so I don't try to cram this all in.
You're going crazy.
All right. So yet another way to write this. Yeah, this could be another matrix equation of the form 1, 1, 1, 5 times C1, C2 equals 1, 3. Okay? And how would you, and one way to solve this is, okay, well, C1 plus C2 I need to equal 1. I can put basically the coefficients of C1 and C2 here, 1 and 5, and augment this matrix and put 1, 3. So this is what's called the augmented matrix. Now, I'm going to talk about how to do a lot of this in a calculator. These just represent the coefficients of C1 and C2 in that order. 1C1 plus 1C2 must equal 1. 1C1 plus 5C2 must equal 3. Okay? Now, what I'd like to know is what C1 equals. And in this format, it would have, I would like to see this matrix as 1C1 plus 0C2 equals something. In other words, if I have a 0 in that spot, then I would know what C1 equals. And just removing the variables, the unknown C1, C2. Okay? And this is what I'm going to show you in your calculators, so we don't have to do this. This is a system of equations, system of 2 equations and 2 unknowns involving C1 and C2. You could do that on your calculator the way I've shown you, but there's also another way to do it using the TI-89. Okay, and let's go to that. I'm going to show you. Where's my big TI? There it is. Okay. On escape. Okay, let's see if I can remember how to do this now. So you can define matrices in here. If you go into apps, data matrix editor, and we want to create a new matrix. Okay. So in type, right click, and we want matrix, hit enter, and call it, go down here to variable. This is confusing, it's not really a variable, we're just gonna give it a name. So this matrix right here, I'm gonna call it just A, alpha A, enter. Okay. Oh, and then we gotta give it dimensions. What's the dimensions of this augmented matrix? Coefficients and the values. 2 rows, 3 columns. So row dimension, column dimension, 2 by 3, hit enter, enter again. Variable is used in reference or changes are not allowed. What did I do?
Just like,
Matrix
just like
name.
any letter.
You call it X over.
What?
I was doing this before.
Depends
What if I
on
call
what's
it
in
a
your
B?
memory.
What's that?
It depends on what you've already said.
But it should, I thought it would overwrite it maybe. 2 by 3, okay, it likes B. Okay, and then, so it opens this up for you, row and column, row 1, row 2, column 1, column 2, column 3, and we got this matrix 1, 1, 1 across. And you could, I think you could hit, well, just hit enter and it goes to the right, right, down, and then down. So 1, 1, 1, 1, 5, 3. Okay. All right, and go to the home screen. And just to check it out, I could hit alpha again and call up B and hit enter, and just to see if it's saved in there, right? 1, 1, 1, 1, 5, 3. Okay. So there's that matrix. Now, the reason why, and we're not getting into the theory about all the row operations you can do, but it was 1C1 plus 1C2 equals 1. Okay. The other one, give me the coefficients. Okay. So this equal sign is like the this bar in the augmented matrix. So what we're doing is, yeah, you can take away, these are just dummy spaces. I can really just operate on the coefficients. I have 1, 1, 1, 1, 5, 3. What I want to know is, I want to know what 1C1 plus 0C2 is equal to, right? That would tell me that C1 equals this. I'd also like to know what 0C1 plus 1C2 is equal to, because that will tell me the solution for C2. Okay? So we want that matrix to be in this form. We want it to look like 1, 0, 0, 1, that identity matrix on the left. And I want to know what's here, because those are going to represent the solutions for C1 and C2. Okay? 1C1 plus 0C2 equals that constant. Okay, so I want to know what it is. Okay, and by the way, in this form, when this is, when you've, after row operations, which we're not going to do because we're going to have a calculator to do it, but when it's in this form, this is called reduced row echelon form, RREF. Okay, reduced row echelon form. Okay, and that's all you need to know, and also how to do it. So, clear? And if you go to math, other math, yeah, matrix. So you define the matrix by going to apps. You do some math on the matrix by going to math. And then go to matrix, and look at this, RREF. Okay, I could also find its determinant. Well, no, that's a 2 by 3. It doesn't have a determinant unless it's a square matrix.
Where's the map button? Oh, it's the
Under 5 in a lot of them. So hit RREF, and I want reduced row echelon form of that matrix B that you just defined. Okay. So 10.5. Aha. In other words, C1 must be 0.5, and C2 is also 0.5. Okay. So reduced row echelon form tells me, that's another way of solving a system of equations. N equations and N unknowns.
You can also do it just directly in
As long as they are linearly independent. independent set of equations. Yeah?
You can also just do it by like directly going into, instead of like defining D and doing that,
Mm-hmm.
right?
Oh, you can define, yeah, there's another way to define a matrix.
And you can just do REF parentheses, then whatever that bracket is, and then first comma, second comma, third, and then semicolon, second comma.
Right, right. Where do you define? Is it up in calc?
No,
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 you
no,
don't
no,
have to define it.
just do REF,
Mhm.
and then do parentheses. And then go to the bracket, which is the comma button, but you have to press second first.
Second.
Square bracket?
Bracket,
Yeah,
Where is the square bracket again? Right here?
yeah.
Mhm.
And then
Okay.
you do,
B?
no, then
Okay.
you just
You
do
can enter
one
it in,
comma,
right,
one comma.
right.
Yeah.
You can enter them all in there and do it
Yeah.
one at a time. If you don't have any other things to do to that matrix B, yeah,
Yeah.
yeah. Yeah, you can do it that way.
Hey,
One,
all day.
comma, one, comma, one, and then,
That's
oops,
a Q. Got it?
questions. How do I get back there without erasing it? There we go. One.
Also, if you have.
And then to make a new column, this is important. You separate entries in the same row by a comma. To create a new column, use the semicolon.
Yeah.
You can also use nested square brackets.
Where is the semicolon?
It's
On the
right.
nine.
It's 9, but
Second
second.
nine.
Yeah, there we go.
and then 9.
Aha.
Oh, I see.
0, 1, 5. 0, comma, 1,
So
comma,
1, 5, 3.
I'm entering the wrong one. 1, 1, 1, 1, 5, 3.
If you have the matrix up there already, like it's 2 before the
Close the bracket.
Yeah, that's a lot of keystrokes.
Oh,
There it is. Okay. You can also go to in the is it F3? No, F2. Anyway, I don't want to look at 3 ways of doing this, but you can also define a matrix by doing define and then putting the entries in and calling it something. Okay. All right. One other thing I want to show you while this is fresh on my mind, I want to hand you is if you haven't seen this before, I have a handout on some handy linear algebra stuff. And with this is specifically with TI-89. This is not theory. Not theory. It is just how to do with your calculator. Equation in terms of systems. Okay. An example of a non-homogeneous system would be, so say x bar prime equals, say px bar plus some other, like f bar of t or something like that. Okay? So, for instance, if it was x1 prime equals a11 x1 plus a12 x2 plus some function of t. Okay, that's one equation. The other equation, if it had, a21 x1 plus a22 x2 plus f sub 2t. So if they tack on a term that involves the, if it involves the independent variable, so that would be non-homogeneous, okay? Where this column of vectors is what we're calling f bar t. Column of vector entries. Okay, right here.
Because right in this, x is the independent, or the dependent variable, and t is the independent variable, in this
Mhm.
example.
Mhm.
Gotcha, so that's.
Yeah, that's pretty
what
common.
t
In
is.
some of them, you know, you'll use x and y, or x, y, and z as dependent, but usually t is the dependent.
Sure.
Because when we get solutions of these, we can also interpret them as components, two components of a parametric function.
Sure.
Right? And that's how we looked at that last time, the phase plane. If we had x, y, z of t, and we found a solution, and we plotted that, that would be a parametric three-dimensional space curve, instead of just in 2 dimensions, x and y. Okay? Why don't we, what time is it, 2:41? Let's take a break, kind of short break. We're going to come back 9.